So we know how to sample. Now let's go to our code, because the code itself, we have the training. So then obviously we're gonna need a sampling file. Okay, so we have the training. We saw this from last time. Now we need some sort of sampling. I think I'm just going to implement my paper then directly, because it's pretty clear. We just talked about this, so we just need to write this. We just need to implement this formula then. So I take my current estimate, I pass it through the model, I multiply with the step size, then I do square root 2 times the step size, times another beta, times the noise power, times fresh sampled noise. And it's a for loop, a double for loop, with L and M, and that's it. Okay, this should be pretty clean then, not too hard. So we need torch, and we just need a function. We're gonna have to functionalize this a bit, and let's say call it sample unconditional, because we just want to create synthetic data. Okay. Let's say it doesn't take anything and it just returns a tensor. We'll have to figure out what the inputs are. Okay, and it returns something. Okay, so we need a number of steps outer, which is an integer, and a number of steps inner, which is an integer. And of course we need the model, I forgot, right? So we need a model, which is a torch.nn.module. Okay, so then the logic would be something like for outer step, for each outer step, then for each inner step, steps inner. I actually have to do exactly what I said. So predict with diffusion model. Okay, so I get output equals model current. Okay, so now what did we say? We have the outer steps, the inner steps, and we pass the model. We're also gonna sample some noise, okay, with the same shape as the output. So I have torch, rand, and like. I don't have to worry about anything else. Then I'm just gonna apply the equation in my paper at the high level, which is I take the current plus the step times the output plus square root of 2 times another beta times the step times the noise power times the noise. Okay, let's see if we memorize that. So apply update step. Update equation. This is the core, right? So we have that current becomes current plus step size times output plus square root of 2 times beta times step size times noise power, no, times noise standard deviation times noise. Okay, that's it. So now we just have to figure out the coefficients. So we know that the step size changes every outer step, and it becomes alpha 0 times r to the power outer step. This is for geometrical progression, okay? Beta is beta, it's just a number. The noise standard deviation is, I have to take this from the outside because it's the noise levels the diffusion model was trained on at outer step. Okay, so now I know more stuff about what I need my input to look like. So I'm also, let me run a so git add src. By the way, this is all on my GitHub too. If you I think the link is also on the Twitch or on the YouTube channel. Okay, do we have nicer formatting here? Okay, so what other inputs do I need? I definitely need alpha 0, which is a float. That's it. I need beta, which is another float. That's it. I need R, which is also a float. That's it. And I need the noise levels, which is supposed to be... Let's say it's a list of floats for now. So I know we need to, let's see, so I need to start. What do I need to start with? Noise levels. I need to start from the first noise level, right? Torch, rand, n. Oh, I think I need an init here, actually. Because I can't guess the shape of this. I don't want to do the shape passing. So I'm just going to start from init. Initialize process. Step size times input towards square root 2 beta times step size times noise standard deviation, which is just the noise level. I guess this is fine for now. Okay, so we're done. We actually wrote the sampling. So then what we want to do is in the training process, let's see. What if I, from MIMO.sampling, import sample unconditional. So MIMO sampling sample. So when do we want to sample here? Run some noise data to get loss function. Pass through model, post process back to complex values. Compute the loss function. Update the model. So then we can say sample from the model. Okay, and we can sample, maybe we don't want to sample every time. There we have to do like a sampling cadence or something. Fine, so then we can call it sampling. So every 100 steps yeah, you're welcome. Thanks for stopping by. Feel free to ask or lurk around or... I see, so we do if step config train sampling verbose. Okay, so then we know we want to sample from, so I need to do the init myself here. So random size. Oh, where do I get the size of the batch? So do I not have the data config? CFG data. Oh, I see, it's here. So data CFG, no, CFG data dot sample size. The thing is, I need to start with complex value here, right? Yeah. So we're gonna have to do torch complex 64. The problem becomes, okay. Well, actually no, because I can just pass it, okay? So samples, val samples equals, what do we call this? Sample unconditional. And how many batch sampling batch. Let's say we sample 4 channels at the same time. So then this becomes sampling batch, no, CFG train dot sampling batch, and I need to unroll this. Okay, so then what do I need to pass here? Come on, show me the thing. Here's the trickery here, because I need to pass the model. Where's the model? Oh, it's just model. Okay. Here's the thing though, because I need to do with torch inference mode, because we want to do this without gradients. So we need to pass the model, the init, config sampling, num steps outer, config sampling, num steps inner. Well, actually, let's do it this way then. Let's just define a sampling config, because I don't want to carry these all the way around. So then we need from data classes import data class. Yeah, so then this only needs to take a config. So then it has num steps outer missing, num steps inner int 1, alpha 0. We have to figure out what this is. This is gonna be bad. Missing our float missing. Oh no, beta float should be 1, because we said this is neutral, right? This is our own invention. The thing is, I need to set alpha and R, and the noise levels are fine. So then I'm gonna have to, I can just pass a CFG here, which is just a sampling config. And then it can be CFG dot, no, config dot, config dot, oh, I don't have missing here, sorry, I forgot. Okay, then I have to leave these untagged. Okay, so the most important sampling parameters are these 3. It depends per university. Yeah, in the US you have to do that. It's a committee and everything. There's no fixed rules though. Okay, so then we have it's inverse problems. It's the thing you see where they use AI to fill in missing pieces or to unblur images. Like even that stupid stuff you see on CSI on like crime shows when they say like enhance to zoom into an image. That's pretty much done with AI these days, with the diffusion models specifically, like super resolution and all that stuff. Okay, so I need a config sampling too. Now the problem is I'm gathering configs like crazy here. I guess we'll take another one, which is sampling config. The thing is, if I do it like this, I need to specify the sampling. So num steps outer. I need to tell something to this. Okay, so we're gonna have to guess the values here. This is gonna be where it's tricky because from what I remember, we had to, and R, I don't remember what R is either. So what do I do here? Okay, I have the learning rate. Then I also need, where the heck do I sample? Oh, so I just need to plot these then, right? Yes. And what's the last missing parameter I need? Oh shit, the noise levels. Yeah, this is the critical one. So what am I training the model on? So the thing, I need to, what am I training the noise? Okay, so we need a strong primitive then, because we need a, so add noise to data. With what standard deviation? Oh, here it is. Okay. So pick a noise level at random. Yeah, so I need to instantiate noise levels. So here it ties into the R and everything. Okay, gotcha. So there is an R float here, which is 099. Okay, I know what's happening here. So it's like max noise level float. Let's say it's 10.0 R, and the number of noise levels, integer. Let's say it's 1,000. So that means I train on all the way from 10 to 10 times 0.99 to the power of 1,000. Yeah, this seems about right. Okay. Okay, so then given these three, this is enough info. And now the R here becomes, it has to be tied. So it ties into the R here. Yeah, because I need to use exactly the same noise levels. Okay, so the number of steps is also given. Config train. Let's just set this to num noise levels. Okay, this is looking a lot better now. Okay, let me finish this. I'll look at what that is. If it's a GitHub link. There's a lot of work on inverse problems though, like hundreds probably. On image reconstruction, all that stuff. Actually, I can do this in post init then. Because I know... Nah, I shouldn't do this. No. So noise levels should be... it should be to model device. No, to model dot device. What should it be? Can I do an easy geometric progression in Torch? So Torch tensor max config train. How can I do this easily? Import torch. Okay, it's taking a while because why? It's finding my GPU or something. Okay, let me see what this... Actually, I'm not sure what's happening here. Huh. If I start, can I do this? Torch tensor 2 times torch range 10. Oh. Is it A range? Okay, so I can't do a progression. So then I can do times torch tensor 0.99 to the power of. Yeah, I can do. Okay, so it's pretty easy then. So it's the max noise level times. Well, actually, I don't even need to do this. It's times. So which one? Oh, it's the base R. Config train.r to the power of torch A range. Config train dot okay, well this looks pretty bad. Let's see, can I get it to pre-commit run all? Yes, I can get it nicer. Okay, so we take the max noise level times to do. Okay, so now here it is. The standard deviation becomes so pick noise levels at random. So now we have to pick a random noise level for each sample. So it becomes is there a torch rand choice? Let's see. Torch random choice with replacement. Can I pick? Multinomial, do I have to do? Each row contains num sample from multinomial. Multivariate replacement true. So then if I do, what was this? Torch multinomial. It's the first time I see this one. These are just standard deviation IDX, and then I just need to pick. Is it really multinomial gives me just indices then? Eek. Noise levels, standard deviation. Oh, is it because I didn't save? I always do this. Okay, sorry. Standard deviation index. Okay, this looks more like it. Okay, so yeah, now we pick indices. So this is just a fancy sampler with replacement. Okay, we have the standard deviation now. We added the model. There's a time step angle here, which we need to fix too, but we'll fix that next time. And that's it. Then we pass the noise. Let's see if we get this. We can add a TQDM bar here so we know where we are. TQDM, import TQDM. And we can do a range here. Okay, so we can just let's see if the sampling works. It should be all tied in now. So we implemented sampling. We also fixed the oh, I see, I need a time step. Okay, yep, there we go. So for now, let's assume time step is 1, but we'll fix that next time because we train with this mysterious variable called time step at 1, 2, which is fine. Somewhere I am missing a, where am I missing? Something is on, not on the model device. Oh, in the sampling, okay. Model. Oh, really? What, the current is in it? Did I not place init on the GPU? I did not, of course, obviously. So device is model.device. There we go, that's it. Let's clean this up again. Okay, so now we should be able to run sampling and the bar should show up and the model will work. Aha, I forgot something very important. I need to convert it to reals, okay? So then we'll say val samples. We need to convert this back to complex. Here's the, because we did this, we have this, right? We have them in data. Complex to real and real to complex. So I need to do complex to real of the init. Okay. And then the samples is I go back real to complex from the samples. Okay. Again, very close now. Because we can't, deep neural networks don't work with complex value data. What is the model output? It's output sample, okay, because we have this UNet. So it's actually not, there is a trickery here because we need to unpack the output here, which is not the greatest thing. I guess we're stuck with Hugging Face, right? Because this is their convention, yeah. Okay, there we go. So we're actually sampling now. Okay, that's it. So we're producing synthetic data. Now, how we evaluate this, it's actually this is harder even than the paper itself because there is no way to evaluate these without domain expertise. And for wireless channels, there are certain metrics you can look at, but it's very hard to tell if these samples are real. But what we can do is we can plot and save them. And we'll do that next time, okay? So for now, yeah, at least we're able to fully generate synthetic data. And we can just check the tensor shape is right, but it should be 4 complex valued channels. And we're very close. We actually wrote sample unconditional, which is we basically implemented 2/3 of the equation from the paper. And that's it. There's another basically conditional term, which will come here, plus some ... plus something. And then we have the paper. So that will be the function called sample conditional. And we have to do some other things with inverse problems, which we'll talk about next time. But yeah, our channels are ready. And there we go. They have the right shape. They're complex valued matrices. The magnitude looks about okay, actually. So it's in the range. And so we'll see what we do with these next time if you're watching on YouTube. So that's it for this part.